Okay, so maybe we can start today lecture. Okay, it's quite a short one. Okay. Oh, I forgot to share my screen. Okay, sorry, I forgot to share my screen. Okay, yeah, please record your attendance. Yeah, for those attended online, yeah, record your attendance. Okay. Okay, so yeah. I don't feel like very fast this semester. I don't know what happens. I feel like this semester is very, very long for me. Okay. So, but I'm very glad this is the last lecture. Okay. Yep. So yeah. So and next week I won't be around. So if you have questions, yeah, if I got time, I will reply you. If I got no time, then sorry, I will not reply. Okay. I need a break. Okay. So yeah. Yeah, wait for today lecture is not very long, not a lot of slide, but we have one case study that we will study. Okay, case study, we study in details. Okay, so this is week 14. We talk about recurrence neural networks. So last week we have what we call the convolutional neural networks. Okay, so it's mostly used for I would say image, or it's a different ways to process data. Okay, to process data as compared to the conventional artificial neural networks. Okay, or the conventional fully connected artificial neural networks. So we have the convolutional neural networks. So today's we have another type of neural networks they call recurrence neural networks. Okay, so basically these two type of networks are already quite some times. Okay, so we have seen some new variants for these two type of networks. Okay, but they are very much still based on these two basic networks that we study. So CNN and RNN. Okay, yeah. So yeah, if you want to know more about deep neural networks, you can always do a project in deep neural networks. Okay, yeah. So what is RNN? Okay, So traditional artificial neural networks are powerful tool for many tasks, okay? But they struggle with sequential data where the order of the input is important. Okay, so far, you know, we can have multiple input, you input together, okay? So basically there's no information about the sequence of the input, okay? So basically all the input that you feed in, they are kind of like equal. Okay, of course you will give different weightage. You will give different weightage to kind of like differentiate the importance or yeah, how they are interrelated. But somehow, you know, the sequence of the input is not included in the conventional artificial networks, and also in the conventional in the convolutional neural networks, the CNN. Okay, so that's why there's a need. Okay, so there's a need to create artificial neural networks that also take into account the sequence. Okay, that take into account the sequence. So yeah, so this is especially important when we have a time series data. Okay, when we have time series data, the sequence is important. We call that sequential data. Okay, yeah. Yeah, another type of data that's important is language. Okay, language, basically the sequence is important. Okay, it depends on the type of language as well. Okay, yeah, because Chinese language, Malay language, English language, or Japanese or Koreans or whatever, they have a different way to create the sentence. Okay, where the order of the sentence is important. Okay, yeah, I bite dog, dog bite me is different thing. Okay, I bite dog mean I'm crazy. Okay, dog bite me, that means I'm unlucky. Okay, so the sequence is important, but in CNN, we don't have these informations. Okay, so dog bite me or I bite dog, dog bite I is the same for CNN. Okay, so but we can still use CNN for this kind of sequential data, but you need some other mechanisms in the neural networks. Okay, so that's why we still see people using CNN for sequential data, but that is where you may need to implement some other algorithms to take care of the sequence. Okay, yeah. So yeah, so how do we have this how do we process this sequential data in RNN is using memory. Okay, so the most important elements, okay, in RNN is the memory, or we call that the internal state. Okay, that is the memory. Okay, that's important. The memory allowed the neural networks to process elements in the sequence. Okay, so while also consider the context provided by the previous element. So that means what happened before will affect what happens now. Okay, but later actually, do I have that? Yeah. Okay. Yeah. I'm not sure. Okay. In fact, the RNNs is also instead of consider the past data, okay, there is a type of RNN also can consider the future data. Okay, so they will use the past and the future to learn what will happen now. Okay, look a little bit science fiction, but that is possible. Okay, because why? Because in the trainings, you have the data already, right? So you have the sequence of data. So that's why what happened now, basically in your data set, you already have the future. Okay, so that's why you can take the past and the future to process now to increase on the accuracy. Okay, so that is more like a bidirectional processing. Okay, so yeah, it's not that if you just say how do we know the future, but in the data set, you really have the past, the now, and the future. So that's why it's possible. Okay, so next, yeah, what happens? Okay, so why we still call it a neural networks? Because it's contain nodes. It's just that the node is slightly different. Okay, so the node is slightly different. So basically, they have something called memory. Actually, the memory is kind of like a feedback loop. Okay, it's kind of like a feedback loop. So that's why the input. Okay, of course, there are some activation functions, and then the next state, we will see that there is two weightage here. Okay, there's weightage here. Okay, one is the current one is the previous state. So that's why if you look at the functions, the current state okay, depends on the future state. The previous state, the current inputs, and also the side of that set of weightage, the weight. Okay, weight. Okay, data, remember, is still the same as CNN. Okay, for every connections we have a weight. Okay, yeah. So yeah. And the difference between RNN and CNN is that, you know, in the CNN, how many connections that you have, every connections they have a weight. It's different weight, if you remember. Okay, in RNN, they will use the same set of weights in every state. So that's why the number of hyperparameter basically is less. Okay, so if you don't understand, it's week 13. Okay, yeah. So yeah, you can see for all interconnected. Okay, so yeah, you can see they have every of this connection, they have different weight. Okay, but in RNN, the weight here, the weight here, the weights all are the same for the set. Okay, so that's why there's only one set of weight for every state. So that means there are only two. Okay, the hash and also the x hash. X hash means the weight for the current input. Hash means the weight from the previous state. Okay, ht minus 1 and also xt. So that is we call the recurrence formula. Okay, yeah. So yeah, so that's why basically it's a feedback loops in the RNN, and this feedback loop provide memory. Okay, the memory of the previous state. So in other words, you know, the previous state depends, the current state depends on the previous state. Okay, yeah. So yeah, one example function that's quite commonly used is the tan functions. Okay, the hypertangent function. Okay, DNH. Okay, I believe you know these functions, right? Okay, yeah, the hypertangent functions. And of course, there are some other functions as well. Okay, Ranu function and so on. Okay, yeah. Okay, so a little bit on the process, just a little bit. Okay, so during the forward pass, they still have the feed forward stage. Okay, so the input at each step is combined with the previous hidden state, ht minus 1. That means the previous state. So that's why the current state depends on the input and depends on the previous state. Okay, the previous state is the memory. It's just that, you know, it's not really that complicated. Okay, yeah. So this process allows RNN to maintain information across the sequence, making it capable of capturing temporal dependency. Okay, that means the sequential. Okay, it's allowed the RNN to capture the sequential, and then from there they can learn the pattern. Okay, similar to ANN. Okay, so it's also involve a process called backpropagations. Okay, but these backpropagations they have a different name. They call backpropagation through time. Okay, yeah. So which is just an extension of the backpropagations algorithms. So do you still remember why we do backpropagations? We want to bring the error back to the input, and along the way we will change the weight so that we can reduce the error. That is the purpose of training. Okay, so that's the purpose of training. Okay, you learn something, after that you compare the difference, you use the difference to adjust the weight so that it's more accurate. Okay, so it's quite a similar process. Okay, so it's quite similar process. Yeah. So because RNN is kind of like a neural network for time series, so that's why they call the backpropagation through time. Okay, BPDT. So yeah, it's still very much the same. So the gradients are calculated for each time step, and then sum up to update the network parameters. Okay. So yeah, so this is I think from here you can look clearer what is INN. Okay, so these are all we call the hidden state H0123. Okay, until HN. It depends on how many layers in the networks. Okay, how many layers in the networks. And the green color, this X1, X2, X3, and so on are the input. So that's why you can see at every state, the current input and the previous state, okay, will go through the functions and calculate what is the next state and so on. Okay, so and then yeah, at the output you will go through another state and you will obtain the output lah. Okay, so this is the feed forward process. Okay, so yeah, so where are the memories? The memories are here. Okay, so these are the memories. Okay, the previous state's memory. Okay, like I mentioned, yeah, I have some things that I write here. So it's possible for us to establish or to create what we call bidirectional RNN. Okay, so that means, okay, yeah. I'm so scared. I thought that is my voice. It's not my voice, right? Okay, so yeah, bidirectional means you will consider the previous stage and also the future state. Okay, you will consider the previous state and the past and the future state, 2 stages. Okay, to shape the current state. Okay, again, like I say, if you wonder how do we know the future, it's all in the data set. We are talking about the training. Okay, your training, you have a sequential data. So that's why basically in the training data set, you have the past and you have the future already. So that's why you can use it to train the models, no problems. Okay, yeah. But when it comes to deployments, how? Okay, when it comes to deployments, how? You don't have the future state. But it doesn't matter, you already trained the neural networks. Okay, it still depends on the current state and also the input, the current input. Okay, it's just the training involve future states. Okay, yeah. So yeah, yeah, again, the output depends on the previous elements and also the future elements. So this is especially important in NLP, natural language processing. Okay, if you use the search engine nowadays, if you type some words, okay, they will give you some recommendation what will happen next, right? Okay, yeah, so that is what is important. It's kind of like you can predict what will happen in the future. Okay, so that's why, and again, we know that in NLP, what is important is not what we say before and whether we can predict what is going to tell if you know next, right? You know, when you have a conversations, sometimes before the sentence finish, you already know what he want to talk, kind of things, right? It's not just that, oh, I understand you, so I know. It's not. It's the nature of the language. Okay, it's the nature of the language. Okay, yeah. So yeah, so that's why in NLP it's especially important. We have these bidirectional RNN. Okay, yeah. So basically, what is special about this bidirectional RNN? Basically, is nothing special. Bidirectional RNN is just 2 RNN. Okay, it's just 2 RNN. One they put in this, I mean, one the direction is this one, the other one the direction is reverse. Okay, so basically bi-RNN is just 2 RNN. Okay, yep. Wow, why? Sorry. Okay, so you can see here. Okay, so this is the architecture of a bidirectional RNN. Okay, so you can see this is the one layers. Okay, the forward layers or the feed forward layers. So basically from the previous state, the current input, we predict the future state. Okay, so this is the backward directional. The backwards directions, okay, the input, okay, is how to say? Yeah, in these directions, okay. So the sequence is reverse, okay, reverse sequence, okay. So you can see this input is feed here, okay, and then feed to the front, okay. So just the direction difference, I believe you can understand, okay. So this is, you know, if this is t equal to 0, this is t equal to n. I do from t equal to n back to t equal to 0. Okay, just the direction is different. Okay, yeah, yeah. Okay, yeah, that is the introductions of the RNN and also the possibility to combine two RNN together to create a bidirectional architecture. Okay, to create a bidirectional architecture. So RNN is commonly known for two problems. Okay, so that both problems related to gradients. Okay, so we call the vanishing gradients problems or also the exploding gradients problems. Okay, so the vanishing gradient problem is something like me. You know, I'm getting older and older. I cannot remember what happened previously. Okay, so you can see as the processing time. Okay, process what happens long time. The memory, the effect of this state in the network is getting less and less and less. So that's why yeah, it's kind of like eventually you forget what happens. You see, the RNN is we want to remember. Okay, when we forget the information, then it's not good. Okay, so we call the vanishing gradients problems. So yeah, you can see here. You can see it's go through many layers. Okay, it's go through many layers. Okay, if let's say the output like here are all small value, less than one, less than one, less than one. Okay, it's small value. You can imagine, for example, 0.1, you multiply with another 0.1, it becomes 0.01. Okay, if you multiply more and more smaller and smaller value, it will become a very small value. So when you take this very small value, you multiply with the previous state, it will become insignificant. So that's why that means this state is no longer significant, is no longer important. Okay, yeah, so this is not what we want. Okay, this is not what we want. Okay, because we want the networks to remember. But when you multiply with a number that will make it smaller and smaller and smaller, it becomes not important. Okay, so that is what we call the vanishing gradients problems. Okay, yeah. Another one is the opposite, sorry. Later. Okay, so another one is the exploding gradients problems. That means this one you only remember what long time ago and you don't remember now. Okay, it's also like me. I always tell the young one, you know, last time we do like this, not like this. Okay, yeah, so it's not good also. Okay, because this will make what happened long before important. Then what happens recently become not important. So it's not good also, right? So when I always say this, then you tell me, sir, this is 2024. You are still living in the 90s, right? So not good. Okay. So this is when the value are larger. When you multiply, it become larger and larger. Okay. So it's two opposite problem, but both will affect the performance of the RNN. Okay, yeah. So we want to find a balance so that you know what happened long before and what happened recently. They kind of like affecting what will happen next. Okay, we want to find a balance. Okay, yeah, yeah. So this is how we solve the problems. Okay, so what we want to say is, you know, we want the networks to be able to learn long range dependency. Okay, that means it can, you know, a long range of memory will still help us to the model to decide what happens next. Okay, yeah, which is important. Okay, so yeah, there are two more advanced networks, okay, that will solve these two problems, are called the long short-term memory, LSTM. This is very common already. Okay, and we also have a bidirectional LSTM. And another one that is also even newer one is called gated recurrence unit, GRU. Okay, so the GRU is a simpler version of the LSTM. Okay, so yeah, but both can solve the gradients problems. Both can solve the gradients problem. How they do that? They use gates. Okay, so just now we have memory, the feedbacks. Now we have something that called gates. Okay, so the gates or the gating mechanism, okay, will help us to control the information. Okay, it's just like a switch to switch on and switch off. Okay, yeah, if we want to forget, we open the switch. We forget everything. So good. Okay. Yeah. Ex-girlfriend, ex-boyfriend, or switch off. Okay. Yeah. So you need to learn that. Okay. Yeah. It's something you want to remember. You close the gate. Okay. You keep the memory there. Okay. Yeah. Then you cry every day in your room and get upset. Okay. So it's good you have a gate, right? Okay. For those who experience lah. Okay. For those who never have boyfriend, girlfriend, yeah, nothing. Okay. Yeah. Okay, so yeah, it's the gating mechanism. The gating mechanism allowed the flow of the information, whether to keep it or to remove it. Okay, so we look at the gating mechanism here. Okay, so the LSTM contains 3 type of gates. Okay, contain 3 type of gates, and also they have what we call a cell state in turn on top of the hidden state. So just now we have the hidden state hash. Okay, now the LSTM they have a cell state. So what is a cell state? The cell state is like a conveyor belt. Okay, the conveyor belt will run in the whole neural networks. Okay, so this conveyor belt contain informations, the previous informations. So it's up to you whether you want to take the informations or you want to block the informations. Okay, so to take the informations, of course you need to feed the information as well lah. Okay, so or to remove the informations, we use gate. Okay, so that's why the gate, we have 3 type of gate here. So we have what we call the forget gate. As I say, you want to remove the informations. You want to discard the informations. You don't need the informations. Okay. And you have the input gate where you feel that the information is important. You want to put in the conveyor belt and share it. Okay. And you have an output gate where you will retrieve the informations. Okay. So you can imagine you have a conveyor belt, the conveyor belt that will move. Okay. And then you can decide to remove the informations. You can also decide to put in information, or you can decide to use the information. Okay, so the 3 gate. Okay, yeah, so that's why you can see here flexibility where you can control. Okay, what information is needed, what information is not needed in the memory. Okay, how to do that? Okay, how to do that? Yeah, you can see this is what we call the conveyor belt. Okay, so the information will be carried in this state. Okay, so this is exactly the just now, the X and the hash. Okay, so I should give, okay, this is the complete one. Okay, but this is the complete one for GRU, doesn't matter. Okay, so not the same, sorry. Okay, so you can see we have the hidden state, like just now we have the hidden state. This is the input. Okay, now we added here is the cell state. Okay, the informations. Okay, so the cell state is added. So this one you cannot see, right? So this is the hash. Okay, this is the X. So the gate are here. Okay, the gate are here. So again, what is a gate? The gate is nothing. It's just a functions. Okay, you take the input, you multiply it with the function, and then you make a multiplications to the previous state. You add on to the informations. So this is the cell state. Okay, so this is the gate. And sorry, here is usually using sigmoid. Okay, using sigmoid functions. Okay, yeah, this is the one it's important. So you can see this is the conventional one. This is the hash. This is the X. And now we added the C. Okay, we added the cell state here. Okay, and then we look at these are the gate. These are the 3 gates. Okay, so the first one is the forget gate. Okay, so the forget gates, yeah, this is again, all these gates are based on functions lah. Okay, so this is the forget gate. It will straight away go to here and will not concatenation. This is just a functions, okay, with the current state. It will just feed the informations into here. And remember here we have a sigmoid. We have a sigmoid. Sigmoid basically is 1 and 0. So the 1 and 0 we decide whether to put in or to forget. So that's why, but they still call this a forget gate. Okay, so it's based on the functions. So the function, maybe this will become 0 or this will remain as 1. Okay, that will decide whether to put in or not. So that is the forget gate. Okay, so this is the input gate. So the input gate, it will take the current state together with the CT. Okay, so it's the two functions here that you can see. Okay, so they will calculate the IT from the previous state. Okay, and then they take the tangents of this state and concatenate together. Okay, so this is kind of like they create a new memory. Okay, they create a new memory, and then you can see here. Okay, this part they still put into the cell gate. Okay, yeah. And last one, so this is the tangent functions lah. Okay, after the tangent functions, they put into the cell state. Okay, so and this is the output gate. Output gate, they would tap the informations from the cell gate, concatenate, do the multiplications. Okay, XOR with this one, and then put in to here. Okay, sorry, this is not concatenation. This is the XOR, the exclusive OR functions. Okay, yeah, and then yeah, so this one you can see they tap the informations, okay, from the cell state to here. Okay, so the 3 stages. And yeah, so the GRU is very much the same. Okay, but they combine the forget gate and the input gate. Okay, they combine the forget and the input gate, and yeah, look like this. Okay, so yeah, they still have a output gate here. Okay, they still have an output gate. They just combine the forget and the input gate, so it's simpler. Okay, so yeah, again, this is just a very short introduction, a brief introduction of RNN. Okay, at least you know that RNN is good to handle sequential data. And why is suitable to handle sequential data is because they have memory. Okay, and yeah, and the LSTM and the GRU improve the architecture. Okay, so that the memory can be kept longer. Okay, in the neural networks. Okay, yeah. So yeah, again, we look at applications. The application is more on sequential data. Okay, so it's more on the sequential data. So where the orders, okay, where the orders of the elements is important. Okay, yeah. So that's why it's suitable for time series predictions, NLPs, speech recognitions. So yeah, and then RNN also can support variable input length. Okay, can process input sequence of variable length. So this is slightly, again, this is slightly different with CNN. CNN, you are processing the image. Okay, usually the pixels and the convolution, you know, the kernel that you want to use, if you still remember, you know, the boxes, you do the convolutions. Okay, you have to map the input. Okay, so that's why for those who are doing project in image, okay, you may need to, how to say, pre-process your image so that it can fit into the CNN. Otherwise, you have to change the kernel size of the CNN. Okay, but RNN is different. RNN, you can take a variable's length of sequence, okay, and put in as an input. Okay, yeah. And then yeah, again, they have the memory, they have the internal state that capture informations. So, and by using LSTM and GRU, it's allowed long-range dependency. Okay, it's allowed long-range dependency. And also allow parameter sharing. So this actually make the models basically is smaller because you use the same weight at every state. Okay, it's not like CNN or the conventional RNN where, you know, every hidden layer you have different set of weight. This you will use the same set in every state. So yeah, if you see just now here, where is it here? Okay, yeah, you can see this one. I forgot to mention data hash, data x, data hash, data x, data hash, data x, same value. Okay, so they share the same set of weight in the state, in the hidden state. Okay, except the output, they may use a different weight at the output. Okay, otherwise these weights are the same. So that's why it's allowed parameter sharing. So you can see it's less parameters. Okay. What decide the size of the models is how many connections. That means how many weights. Okay. So you can see this is definitely smaller as compared to the conventional one. Okay. But of course, if you have, yeah, it's smaller. Okay. Yeah, that is on parameter sharing. Online learnings. Okay. Yeah. So because you are fitting the sequential data. So that's why the learning is based on the sequential data. So this is also very good for online learnings. Okay. While learnings, while doing the trainings and then the deployments. Okay. So it's kind of like they have the capability to keep learning. Okay. When you have more going in, you will keep learning. So this is a little bit like your ChatGPT as well. But of course, ChatGPT is using a different mechanism. Okay. ChatGPT actually, you know, every time, sometimes they will ask for your feedback. Do you use ChatGPT? Yeah, for your assignment report, right? Yeah. Okay. So when you use ChatGPT, sometimes you see after they generate the what they call the output, your answer, they will ask for your feedback, whether this is a good or not a good one. Okay. So this is a little bit like reinforcement learning. They will learn, they will learn. Okay. But RNN is kind of like keep learning. When you have new data coming in, they can keep the data and keep training the models. Okay. So that's why this is quite suitable for sequential data. For example, you know, our weather. Okay. Most of the times, every year, more or less the same. But over the last 10, 20 years, you will see that there is a trend. Okay. Maybe getting hotter and hotter. Okay. So yeah, so INN has the capability to, you know, you train using early data, you use it when the data keep coming in, they can keep learning. Okay, and update the model. This is quite important. Okay, yeah. So and also INN, actually this is not just the strength of INN, instead CNN also. So they are keep evolving. Okay, so that's why the CNN, they have the graph neural networks also. Okay, yeah, so the GCN and so on. So it keep evolving. Okay, so for INN we have the LSTM, we have the GRU. I think this is the two only. Okay, variants of INN. Okay, so it's good enough. I don't see any new ones. Okay, yeah. So yeah. So again, the application domains, NLP, time series predictions. Yeah. So the stock market cannot predict lah. Okay, yeah. The weather we can forecast. Okay, yeah. And then on speech recognitions, speech to text, text to speech. And then on sequence modelings, gestural recognitions, that means the movement. Okay, the sign language and the movement. Okay, yeah. For example, I take something, I want to have this movement. So am I going to throw this and hurt you or what? Okay, so yeah, there are some research on that also. Okay, so yeah, on music generations, so we don't need songwriter anymore. Okay, yeah. So yeah, even ChatGPT can write song. And then in biomedical healthcare monitoring diagnosis, and then yeah, autonomous driving. Okay, all these are sequential. Okay, all these are sequential. So yeah, okay, so yeah, I have two examples, I think, for week 14. Okay, the first one, I try to find a very simple RNN implementations, but the example is too simple. So that's why I don't even want. So that's why yeah, you can look at these examples that I include both LSTM and GRU for the stocks market history or predictions. Okay, so it's also quite a simple examples, and you can compare this with the time series. Okay, the ARIMA models that we do in week number 11 or 12. Okay, forgot 11, I think 10. Okay, yeah. So you can, it's very much the same functions. Okay, yeah. So today I want to focus on this video classifications. Okay, I want to focus on this video classifications. So yeah, I think it's based on this one. I know it's based on this Keras. Actually, the data cam also based on the Keras, this example on video classifications. Okay, so yeah, I want you to run the examples, and it would take quite long time. Okay, it depends on how powerful is your machine. Okay, so yeah, but I confirm that can run. Okay, so I want you to run this this code. Okay, yeah, it will take some time. While running, you can take a break later. Okay, yeah, when you come back, I think it's still running. Okay, so now you just run it, and I want you to do a case study on this video classifications. In these examples, I combine both CNN and RNN. Okay, not me lah. Okay, this example is combine both CNN and RNN. You see, in video classifications, what it's doing is, you know, from the videos that we watch, we kind of like know what kind of motions, you know, yeah, or what type of the genre of the movie. Okay, so this is important. Okay, so yeah, it's just like, you know, you go YouTube, you watch one type of movie, and then the recommendation give you all similar one. So, you know, yeah, you have to watch all because they are, you know, they know your interest. Okay, so this is part of video classifications. So and also this is important also when we do you know, we want to classify the movie. Okay, we don't ask everyone to sit, we don't like employ many people sit there, watch the movie, and then do the classification. That will be too slow. Okay, previously they do that lah. Nowadays the AI, the deep learning can help you. So this is the video classifications. Okay, so on one hand you can see that the input is basically image. Okay, video basically is image. Okay, video is the image that play at certain speed. Okay, most of the time is about 25 to 30 frame per second. Okay, so in every second our eye is processing 30 frame, then only it look like a movie. If it drop below 25, our eye cannot really notice. We still see that as a movie. If it drop below 25, for example, you have only 20 frames per second, you will see that movie is like a slow motion movie. Okay, so and if you watch at very high frame per second, 40, 50, yeah, very likely you will be admitted to hospital, and you don't know what is the reason. The reason is our eye is processing. It's very tiring for us. Okay, so there's a case. If you know the Pokemon, you know Pokemon. A long time ago, one of the episode they broadcast, I forgot what is that. What's the name already? Polygon, is it? The Pokemon is called. That episode, because they are making the cartoon, right? At a higher frame per second. I forgot how many. Actually, many kids admitted to hospital or not feeling well. Okay, yeah, because of that. So yeah, we can use movie to kill people. Okay, yeah. So yeah, so that's why we can see video basically is frame, is picture. Okay, so picture. So the best way to process picture or for us to understand what is inside the picture is using CNN, right? But videos is sequential. Am I right? Yeah. If you take the video, the frame, you randomize the frame, you will not get a movie. Okay, yeah, you will just get distortions. Okay, so yeah, for that sequence you need RNN. So that's why this is the best way is you combine both CNN and RNN. Okay, so I want you to look at this example. You run the code and you look at, you know, how to do a video sequencing and then using a CNN and also the RNN. And another questions that I want you to try to look for answer is, can I simplify the model by using just CNN or just using RNN. Okay, so yeah. So yeah, that is what I want you to do. But and then I just provide a little bit on the video notes on video classifications. Okay. So yeah, what is video classifications? Is involve assigning a label to a video clip and then integrate what actions or event is happening. Okay. So yeah, so from there, you know, some application includes surveillance. Okay, include sports, analyze the movements, and then yeah, and then also in autonomous driving. Okay, understanding the route scenario. So the challenge here is the temporal dynamics. Okay, the sequence. Okay, the sequence, and then yeah, some other challenges is also involve the high computational cost, because you want to process one image is already challenging. Now it's a sequence of images. Okay, and then yeah, the data size is very large. So these are all the challenges. So key considerations in model selections, you have to look at the data characteristics. The volume is large. Okay, the variability is diverse. Okay, so and then computational resources, the hardware needed. Okay, and also the training time required. And then also we need to consider on accuracy and also efficiency. Okay, accuracy is how good is your classifications, because we're doing classifications. Okay, efficiency is how fast you can do it. Okay, and how much resources you need to do it. Okay, so these are the considerations. So that's why yeah, deep learning has shown a great promise, or have developed some very good models for video classifications. Okay, so using CNN, using RNN, okay, and some variants of CNN, such as the 3D CNN. Okay, and we have graph neural networks, we have graph convolutional networks. Okay, yeah. So yeah, they have a little bit of explanation how they do that. Okay, we can also consider a two-stream networks that consider spatial and temporal features separately. Okay, so the two-stream networks, or we can use transformer as well. Okay, transformers is something that we didn't cover. Okay, transformer is currently kind of like the most advanced deep learning's models. Okay, and especially good in image. Okay, transformer. Okay, and we can also have hybrid models. That one in the examples combine the CNN and RNN. Okay, yeah. So yeah, these are some paper on the video classifications. If you have time, you can read this to prepare for the questions. Okay, or later you can try to search this paper. Okay, when you read the paper again, you do not need to read the whole paper. Okay, you read the introductions, you read the conclusions. You may want to go even in the introduction, you already know how they do it. The method is also in introductions. Okay, so that's why this paper, you can try to look at the introductions, how they do the video classification. And basically the one I choose is difference method. Okay, different method. Okay, so this is how to evaluate classifications. It's still based on accuracy, based on efficiency and robustness. Okay, so yeah, I finished the lecture already. So that's why next is the activities, and then yeah, then we will have a discussion again on this video classifications at the end of today. Okay, so yeah, what I want you to do first, I want you to run the code. I want you to run the code, and I want you to study a little bit on the code. The code is actually very short. Okay, it's very short, but it's quite powerful. I just want you to see how we can combine the CNN and the RNN models, okay, to do video classifications. Okay, the second one, since we only study CNN and RNN, so that's why all this method that I show you is just for your you know, knowledge only. So that's why the focus is still on RNN and CNN. After you look at this code, you look at how they are implemented, and this one is a hybrid model that combines CNN and RNN. I want you to think, how can we or can we do this by using only CNN or RNN only? Okay, I don't want a hybrid models. I want a standalone models. Okay, so I want you to find answer how to do that by using only one models. Okay, so that is second part. So after you have that single models, I want you to look at where is it? Yeah, I think this part. Okay, so yeah, I want you to consider, is the model, the standalone models, how good is it as compared to the hybrid RNN CNN model? Okay, and basically I believe you can tell that the standalone model will not be that good as compared to a hybrid models. I want you to identify where is the difference, where is the limitations. Okay, yeah. So this is what you are going to do in group. So and also together with the break, I will come back at about 2 o'clock. So yeah, because you run the code need quite sometimes. Okay, and yeah, there's quite a lot of discussions I hope you can do. Okay, so all these are included, not included, is to prepare you for the question 3. Okay, your question 3 is video classifications. Okay, so now you are searching the information for your question 3. Okay, yeah, so I will come back at 2 o'clock for the discussions. Okay, yeah. There's no problem, right? You have internet access here, right? Okay, and anyone need this one? Yeah. Yeah, just send email to me. Assignment, right? Yeah, just send email to me. If you just send, I will mark when I got time. Okay, yeah. Okay. Okay, so nobody need this,
Whether if functions are the key to change the weight.
They don't change the weight is back propagations. When back propagations, they will change the weight. Yep. They will change the weight back propagation.
People will tell you that twice to talk to
Sorry again. You talk to the Aisha. Okay, that's good.
I just want to tell you so there is no miscommunication.
There's
That you have said if it could be myself.
she rejected.
No, she accepted.
She accepted. Okay, that's good. That's good. Okay.
Tell you that.
Oh, okay.